Okay, so we've learned a couple things here. So I'm going to use... Okay, that's going to be a north pole of a magnet. Go blue. South pole of a magnet. Okay, we've learned a few things so far. Okay, we've learned about an electrical current going around a wire. Okay, so let's say we have a wire here. So we have a copper wire here. Okay. The magnetic field is going to be circular around this. So if we take that view and we make this copper wire run as if it's coming towards the page, okay, so we cut that wire and it's coming towards us, the magnetic field is going to be circular around. Okay, so we can make a magnetic field, right? Secondly, we also talked about, okay, we can induce electricity. Okay, but it requires a magnetic field. Okay, we can induce an electrical current. So let me take this example again. So we have our magnetic field, okay, and we have a wire. So let's say that wire is, no, I don't like that. I'm not a good drawer. Okay, so let's say this wire is just right there. Okay, if we take the wire and we move this wire up and down, okay, the wire will produce an electrical current. Okay, now the big thing is, remember that it's between a magnetic field. Okay, if you physically move a wire between a magnetic field, okay, there will be an EMF produced and there will be an electrical current that will start to form. Okay, so those are the two things we learned about so far. We have electrical currents, okay, being produced, and we have magnetic fields being produced as well. Okay, so let's get going with, how does force play into here? So let's say that we have North Pole and a South Pole. Okay, the magnetic field lines run from north to south. We should be familiar with that. Okay, I'm going to keep these here. The highlighter's a little faint. That way we can continue to see the motion, okay, or which direction the magnetic field is moving, working, so to say. So let's say we have a wire here. Okay, now we have a magnetic field. Okay, so we don't need to produce a magnetic field. Then we turn this wire on to where now an electrical current is flowing through the wire. Okay, so we have a wire with a current flowing that is placed inside of a magnetic field. What is going to happen? Or what do you expect to happen? Okay, it's not like we're looking to produce a magnetic field with a current. We're not trying to produce a current, okay, by moving it in a magnetic field. We have both. Okay, and what happens, okay, is there's a force now applied and produced. Okay, and this force, we'll do green for force. This force is actually going to push this wire up. Okay, so there's going to be a force up on this wire. Now, after this, there's a good video I want you guys to watch. It shows you another right-hand rule. So we have our first right-hand rule, which allows us to determine the direction of a magnetic field around a wire that's carrying a current. So if we had simply the wire here, no magnetic field, okay, and we turn that wire on, we know that the magnetic field produced, which I showed earlier, it's a circular in shape around the wire. Okay, if you point your thumb in the direction of the current, okay, and wrap your fingers around that wire, your fingers that are curling around the wire, okay, is the direction of the circular path of that magnetic field. Okay? Now, our third, we're actually skipping the second right-hand rule. We're going to the third right-hand rule. Is going to show you the force, okay, produced in a current that's carrying, or a wire that's carrying a current that's placed within a magnetic field. Okay, so we'll watch that video a little bit later. Okay, but here's a very big principle. That green arrow is a force, and it's going to push this wire and have a force on this wire moving up. Okay? Assume that copper wire is kind of like I said, running through the page here. So I'm going to take my copper wire, I'm going to make it big, I'm going to cut it, and let's say that this copper wire is running right through the page towards me. Okay? This force is going to be applied upward on that wire. Okay? So, what is the importance of this? Okay, and that's where I want to clear all this. Okay? So that's where we're going to look at a galvanometer. Okay? So galvanometer, you have your, oh my god, you have a solenoid there, which is your coiled wire, okay? Oh. Electrical wire, and let's say we have our galvanometer here. Okay, and we have the needle of the galvanometer. Okay, and again, the galvanometer moves both left and right. Okay, so here's our galvanometer. And the other day I asked you guys, I go, how does the needle move? Okay, what's the importance of the needle and why does it move? Okay, now if you remember, we'll say that, no, orange is the name, copper, let's say blue is the magnet, right? Again, we said if we move this magnet in and out of the solenoid, okay, an electrical current's produced. Make sense? Okay, so an electrical current's being produced. So if we go here, I'm going to draw our magnetic field again. Okay, so we'll say red is north. That's going to be too close. We have our south magnet. Okay, just to remember, we got north and south. Okay, so how a galvanometer is set up, okay, is you guys see these wires attach in here, right? Okay, but inside, okay, that's what we're going to break down. Inside the galvanometer, okay, these wires are going to form what's called an armature. Okay, so it's a wire that kind of goes like this. Oops. Here, comes out, comes here, goes like this. Okay, so we have our armature. Now again, this yellow, this orange, I should say. Okay, this is a wire. Okay, and these wires are then connected to the two red wires that are coming from the solenoid. Make sense? Okay, so we said it depends upon which direction we move the magnet inside our solenoid, which will depend which way the current flows, right? We said in our video that galvanometer predicted that there was currents from both ways. Okay, if you move the magnet from right to left, then the current flows one way. If you move the magnet from left to right, the current's going to flow the other way. Okay, so just please remember that. So we have a current that could either be coming into the galvanometer from this direction or into the galvanometer from this direction. Okay, the current could be either direction. Okay, and that's going to be important here. Okay, that's going to be very important because that's going to be why the needle moves either one way or the other. Now, we said, okay, that if we have a current, okay, running through a wire that's placed inside of a magnetic field, a force is produced, right? Okay, so let's erase this side. So let's just assume that the current is coming in from the left. Okay, the current's going to flow through the copper wire, okay, and then all the way out back. So now this current's going to be going here, okay, and coming back out. Okay, so you guys are following this current. Now, again, we have a current flowing through a wire in a magnetic field, so a force is produced. Okay, and a force is going to be produced on this side of the armature. Okay, and actually, okay, which we'll learn also with the right-hand rule, since the current is flowing this way on the right-hand side, it's going to produce a downward force on this side, okay, of the fork. Now, if you have an upward force and a downward force onto something, it's going to cause it to rotate, okay? Which is perfect because there is a circle connection here that allows this device to rotate. So now, this device, okay, we have right here, so at this point would be the needle. I'll draw it like this, would be the needle, okay? So depending upon which way this armature turns, okay, the needle is then going to act and be turned either left or right. Okay, so now a galvanometer, again, only identifies small electric currents. Again, if you move the magnet, the current is only going to be in for a little bit, so that needle is only going to move a little bit one way, okay? And then, so let's say that the current flips and we move our magnet in the opposite direction, right? We're going to move the magnet now back, which means our current's going to flip. Okay, so let me try to get a drawing for you. Okay, so now the current's coming in this way, it's flowing this way, and back out. Okay, so we move the magnet the other way. Okay, so now we know that the current going this way is going to produce an upward force, and the current going this way is going to produce a downward force. And again, it's going to cause it to rotate in the opposite way. Okay, does that make sense, guys? So that's the reason why a galvanometer works so well to produce or to predict, okay, and a measure, that's the word I was looking for. It does a really good job of measuring small currents. Okay, because as I said, if you have a current inside of a magnetic field, okay, there's going to be a force produced. Okay, and that force produced is then measured by the galvanometer, and you can see the needle moving one direction or the other direction. Okay, so that's the physics behind the galvanometer. Now, what this is called, okay, that's going to be called an armature. Okay, a galvanometer is a one singular armature. Okay. Now again, also notice the other issue with a galvanometer is that it's not a constant current. Okay, the only way that you're producing a current in a galvanometer in this setup, okay, is with the magnet, which only allows you to produce short bits of current in one direction, and then you got to move the magnet through the other way, okay, which produces a current in the opposite direction, which is why you see, the alternating current, okay, alternating the needle both left and then right. Okay, does that make sense, guys? So this is an armature. In the video that I'm going to have you guys watch next, okay, it does a pretty good job of explaining the different right-hand rules. Now, you can use the right-hand rules, and it does a good job of showing it, okay, to predict which way is the force going to go. Okay, because again, big thing, the direction of the current I showed you flips what direction the forces are acting, which is in turn going to turn, okay, this armature one direction or the other direction. Okay, now this is the principle behind all electric motors. Okay, what if I said that this current didn't turn off? What if we had a battery hooked up and this current was going to be flowing through constantly? Well, then those forces are going to be applied constantly as well. Okay, there's more to it. We have to talk about, the split rings and how the split rings allow the current to continuously flow in the same direction. But okay, this principle here, okay, that force acting, turning, okay, this is the force, or is the same forces and the same principles that turn electric motors. Okay, that's why they're called electric motors. If you need a battery, and once you turn it on, let's say we're looking at an electric drill, which we're going to show videos and talk about. You attach a battery to the electric drill. Okay, that battery produces a current flowing through, okay, the wire like this. Inside that motor, there's a magnetic field. Okay, and if you have a constant current, this force is constantly being applied. And if this force is constantly being applied, okay, that motor is just going to keep turning and turning and turning and turning. And you see a drill, okay, the top head just keeps turning and turning and turning. Okay, in a simplistic version, that is an electric motor. Okay, obviously, if you guys are having a tough time understanding this, okay, I'm going to try to give out more visual demonstrations and video walkthroughs explaining this material.